Welcome to the session Ensembling. In this video and the following videos, we will learn about Ensembling and how it connects to automated machine learning. So first, what is Ensembling? Ensembling combines the prediction of multiple models to create a so-called meta-model or ensemble model. Ensembling can make weak learners strong, and it can further improve strong learners. Importantly, ensembling is an alternative to picking a single model, so it circumvents the model selection problem. In practice, it often outperforms picking a single model. On the right-hand side, you can see a simple illustration of how ensembling works. For a training data set, we train a total of m different models. And then we gather the predictions of these models, make an aggregation, which would then be the final prediction. For test data, it would work the same. We have the trained models, and then we input the data, we obtain the predictions, we aggregate them in order to obtain a final prediction. The key choices in ensembling are then how to obtain the base models and how to actually aggregate them. And this is what this and the following videos are about. Why is ensembling interested for automated machine learning? An AutoML system, or also a hyperparameter optimization method, evaluates many strong models, but different models. And selecting a single winner often discards useful information. Ensembling thus combines the predictions to improve robustness and performance, and it can directly work on the output of the AutoML system or hyperparameter optimization method. And ensembling can also reduce the sensitivity to noise and noisy validation estimates. Before actually going further into this, let us recap two ensemble methods that you should be familiar with from your Introduction to Machine Learning courses. The first one is bagging, which is a portmanteau for bootstrap aggregating, and which is a very well-known and often used method. It works as follows. First, we sample the training data with replacement multiple times. Let's say we want to sample k bags. Each of these bags has the same amount of training data as the original training dataset, but slightly different because some data points are repeated multiple times, while some other data points are left out. Then we train base models in parallel, so each base model we train on one of the bags, and then in the end we aggregate the predictions, usually via a so-called voting mechanism. If we obtain new data, we simply take each of these models, make a prediction, and aggregate the predictions in the end in order to obtain the ensemble prediction. This is an example of a so-called homogeneous ensemble, where we only use models from the same model family, and we induce differences in these models by actually changing the training data that the models are trained on. A famous example of this model class are backed decision trees. Here we simply take standard decision trees and apply them to the backed versions of the trained data set, these bags. Another method is the random forest, that's more often used in practice, and here additional variance in the models is induced by also sampling a random subset of the features where the splits are chosen from in every split point. So what does this do in practice? So for this we will have a look at the bias variance decomposition, first of a single tree and then of the backed decision tree model, or backed decision tree ensemble. And we remember the bias variance decomposition decomposes the prediction error of a model into bias, variance, and noise. We can see in the top facet the function that we want to predict, the blue line, and some samples drawn from that. These are the black dots, these are the values of the blue line plus some noise. Then we have the prediction of a single tree. This is the red line. And we have also in turquoise drawing a data set from the underlying function with noise and training a decision tree on it. We can see that it actually averages out with the actual underlying function. We can now try to understand how a single tree or how the error of a single tree actually behaves by doing the bias variance decomposition. And we can see that the error, that is the magenta line, actually decomposes into, as mentioned above, bias, variance, and error. That the error is more or less constant across the whole range X. We have very little bias, so we can actually approximate the data quite well, but we have a high variance, especially around -0.5 and around 3. So this is where we have little data, or where we have somewhat conflicting data, and multiple draws of a model will actually result in slightly different models that contradict each other. If we now repeat the bias variance decomposition actually for backed decision trees, we can see that we obtain a lower error. And this lower error, when we decompose it, mostly can be explained by having a lower variance. We have a slightly higher bias because the individual models are a bit worse than actually training one model on the full data. But we traded off bias for a large reduction in variance, which overall leads to a drastically reduced prediction error, which is an explanation why these backed decision trees, or in general backed models, work so well. Another method that you should be familiar with is gradient boosting. In gradient boosting, we train additive ensemble. This means every model works on the output of the previous model, so we build like a stack of models, and each new base model is fit to the negative gradient of the loss of the previous model. So we try to correct the output of the previous stack of models with a new model that we add on top. And for squared error, this is very convenient. This is equivalent to fitting the residuals, so the differences between the actual function value and our prediction at the current modeling stage. Popular implementations of gradient boosting are XGBoost, LightGBM, and CatBoost. And these are popular and well-working methods for tabular machine learning, where they are actually applied on a daily basis. Now, in order to simplify introducing more ensemble methods, I want to briefly extend the notation that we used so far by some ensemble-specific notation. Generally, we're interested in combining m different models trained on training data D, and each of them has a hypothesis space out of which we obtain the model, the actual implemented model and trained model f hat 1 to f hat m. When applying the model to new data, we can obtain two kinds of predictions. First would be probabilistic predictions, the probabilities for different classes, which we denote as p hat m for the mth model, and y hat m, which for classification are the hard labels, so 0, 1, 2, or for regression, the actual prediction. And finally, we need an aggregating function g that takes multiple models, 1 to m, and outputs the ensemble. Now let's have a look at how this looks for model averaging. One way to average multiple models in classification is so-called voting. And here we take the output of each of the individual models and simply count how often they cast a vote for a different class, and then simply take the class for which most votes were cast, so which was picked by most models. This is called majority voting, sometimes also hard voting, because we have the hard labels. We can also use model averaging, sometimes also called soft voting, where we take the probabilities of the individual models and we average them. Then we obtain new probabilities for every class. If we want to make a prediction for a classification there, we would simply take the argmax of that. And otherwise, we can simply continue working with the probabilities vector. For regression, it's much simpler. There is only one way to average the the output of the models, namely by averaging the prediction of the individual models. Model averaging is often used to average models from different families, then called heterogeneous ensembles. To summarize, in this video, we learned that ensembling combines multiple models to improve robustness and performance, and that we want to use this in automated machine learning because in automated machine learning, due to the hyperparameter optimization, search, or general other search procedures, we obtain a library of models, and only using a single one would be actually wasteful. We recapped that bagging mainly reduces variance, while boosting learns sequentially from errors. And we had a look at hard voting, soft voting, and averaging as aggregation strategies in ensembling. See you in the next video.